In this video, we're going to be solving Leetcode question 33, which is search in rotated sorted array. Let's get started. So in this question, we are given an array that is said to be rotated sorted. What this means is we started with a sorted array sorted in ascending order, and then a pivot index was chosen within this array. So in this case, the pivot index would be here. And then to rotate the array, we basically take all the elements that are to the left of the pivot index and move them to the end of the list. So now the list starts with 4, 5, 6, 7 and ends with 0, 1, 2. However, we don't have this original sorted array. We're just given this rotated sorted array. We are also given a target, which is an integer value, and we need to find this target value within our rotated sorted array. So we need to look through the sorted array and return the index of the target value. So in this case, the index would be 4. And in the case where the target value doesn't exist in the rotated sorted array, we would just return -1, which means that the target value wasn't found. The obvious solution here will be to conduct a linear search throughout the sorted array until we find our target value. So since our target value is 0, we're just going to go through the sorted array from left to right until we find the target array. So we look, we don't find it here, 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 or here, but we do find it here, so then we're able to return that it's at the index 4. This solution is going to be O of n time, and the reason why is because in the worst case scenario, we're going to have to check through each and every element in the list to guarantee that the target value is not anywhere in the array. The obvious inefficiency with the solution is that we don't take advantage of the fact that the array is already partially sorted. Now, if the array were completely sorted, then we could use binary search, which would involve looking at the middle index of the array, and then depending on whether the target value is smaller or larger than that middle index, we can cut out half of the array and then narrow down the search space like that. So if we can find a way to convert this rotated sorted array into an actually sorted array that goes from ascending order, then we could apply a binary search algorithm, and maybe this will be a lot more efficient. Okay, so how do we go about converting this rotated sorted array into an actually sorted array? Well, first, let's do a little bit of analysis on what a rotated sorted array will look like. The array smallest value is going to be somewhere in the middle of the list, and we don't know where. Obviously here we do because we can actually see the entire list. So it starts somewhere in the middle, and it's going to increase until we get to the end. And then it wraps around to the start. So that means the start value is going to be bigger than the end value. And it's going to continue going forward until we get to the element right before the one where we started. So 7 is the biggest, and then right after that, 0 is the smallest. If we were to graph the array in terms of how the elements change over going from left to right, it's going to look something like this. It starts at a point, and it goes up until we get to the peak element, and then it goes back down abruptly until we get to the bottom element, and then it will keep going up, but then not to the same extent as before. So if we draw a dotted line here, the end of the array is still smaller than the start of the array. With that in mind, our game plan now is to find elements in the interior of the array and compare them to other elements in the array, and then from there try to deduce where the pivot index might be. So right now we know the location of the first value in the array and the last value in the array. Let's take a look at a random value in between them. So let's say 6. We're going to compare 6 to the two elements we already have, which are 4 and 2. So 6 is bigger than 4 and it's bigger than 2. What does this mean? Well, 6 is in the middle and 2 comes at the end of the array, but 6 is greater than 2. How can this happen in a sorted array that is ascending in order? It can't. So what's going on here is that there must be some sort of break in the sorting. At some point between 6 and 2, the values stop going up and then drop to a lower value. And this is exactly the pivot index we are looking for. So given this one fact, that 6 is bigger than 2, we're now able to deduce that the pivot index must be somewhere in this portion of the array. Now let's take a look at another example. Let's take a look at 1. And again, we're going to compare it to 2 and 4, which are the two elements we have right now. 1 is both smaller than 4, and it's also smaller than 2. 1 is smaller than 4, even though it comes later than it in the array. So that means, again, there must have been some sort of break between 4 and 1. If there wasn't a break, the numbers would continue going up, and then 1 would have to be bigger than 4. So that means there must be some break, or in this case, a pivot, in this portion of the array. And hopefully now you get the picture of how we're actually going to find this pivot index. So what we're essentially going to do is apply the binary search algorithm 2 times. First, we're going to apply it to straighten out this rotated sorted array, so we just get a plainly sorted array. And then afterward, we use the binary search algorithm to actually find our target in the newly sorted array. So just like the regular binary search algorithm, we are going to start with our left and right pointers at the beginning and the end of the array, respectively. We're then going to find the middle between those 2 values. In this case, it would be the index pointing to 7. And then we would have to check whether 7 is a pivot value. The way we do that is comparing that value to the previous value in the array. If 7 is less than the previous value, then that means it must be a pivot index. But in this case, it's not. So now that we know that 7 is not a pivot index, we need to find which half of the array the pivot index lies in. So now we have to compare 7 to our left and right pointers. 7 is both bigger than 4 and it's bigger than 2. So since 7 is in the middle of the array, but it's bigger than an element on the right side of the array, that means there must be some sort of breakage in the sorting between 7 and 2. So now we can limit the search space to here. And then we do this again. So now 7 becomes a left pointer and 2 is still the right pointer, and the pivot index must be somewhere in this range. So now once again, we find the middle between these 2 values. In this case, it will be 0. We compare 0 to the previous element in the array, and we find that 0 is less than 7. So that means 0 itself must be the pivot index. The pivot index is right here. So now we can take this half of the array and place it in its desired spot, before all the other elements. So this becomes 0, 1, and 2. This goes away, and now we have a fully sorted array. Now, all we have to do is apply the binary search algorithm one more time to actually find where our element is. And we're done. This solution is going to take O of log n time. The binary search algorithm typically takes log n time because every time we do a comparison, we're able to cut the search space in half. We have to do 2 binary search iterations, one to get the sorted array and another to find the target value within that sorted array. So technically it's O of log n plus O of log n, but that simplifies to O of log n time complexity. So now that we have the optimal algorithm, let's code it up. If you're finding these videos helpful, I think you'll love what we got going on in our private community. We dive even deeper with exclusive content that won't be shared on the main YouTube channel. I also offer individualized coding interview study plans that are tailored just for you. You can also join small group sessions, participate in mock interviews, and get your questions answered in live weekly Q&As. It's a great way to take your coding interview prep to the next level. If you're interested, check the link in the description below. I'll see you inside. All right, so this is the Python code for solving search in rotated sorted array. First, I start with a simple if statement, which is going to handle the case where the list we're given has 2 elements or less. Because in that case, the binary search doesn't really work as intended. Assuming that it has 3 or more elements, I'm going to do the first binary search, which is going to find our pivot index and straighten out this array. So I set my pointers and I initialize pivot to -1, and then I perform the binary search. It is going to look at 3 cases. The first case would be if the value we just looked at happens to be a pivot index, and we're going to set the pivot value to that index. If the value is less than the left pointer, then that means the pivot index must be in the first half of the array, so we set the right pointer, and otherwise it's going to be in the second half of the array, so we set the left pointer. Then once we find our pivot index, we are going to straighten out the array until we get the nums sorted. So this is a perfectly sorted from least to greatest. And then we just do the classic binary search to check if the element exists. So we set our target index and our pointers again. We do the exact same binary search algorithm mostly. And if the target is equal to -1, we return it. And otherwise, we are going to take the target index and then add the pivot and then take the mod of that value. And the reason why is because when we convert from the rotated sorted array to the real sorted array, the elements get jumbled up in terms of the indices. So to correct for that, we add the pivot and then take mod by the length of the array. So this makes sure that the index corresponds to what it was in the original array as opposed to the sorted array. So now let's run the code. Passes all the cases and click submit. There you go. That is the solution.